We're going to start talking about aldehydes and ketones. And in order to do that, we first have to discuss the carbonyl or carbonyl compound. So the carbonyl group is a group that's a carbon doubly bonded to an oxygen. And generally that then gives it, along the carbon, it'll give it a bond angle of 120 degrees Celsius because we have the groups here and here and here, and those, remember, those electron domains like to kind of repel each other. So 120 degrees is 360 divided by 2. Now, because of the electronegativity of the oxygen, we're also going to end up getting a partial positive charge here for the carbon, and we're going to be getting a partially negative charge for the oxygen. And so this gives us some electronegativity differences and polarity within these groups. There are a number of different functional groups that are actually going to have the carbonyl group, and those include aldehydes and ketones, carboxylic acids, esters, and amides as well. You can see the difference between these are that the aldehydes, instead of being attached to another R group or another part of a chain, this is at the end of the chain, right? This carbonyl group is at the end of the chain and it has a hydrogen attached. Acetaldehyde is an example of one. A ketone is where this carbonyl happens in the middle of a chain. Carboxylic acid is where it happens at the end of a chain, but we also have this alcohol, this hydroxyl group, attached to this carbonyl carbon. So that's an example of that. A simple example is an acetic acid. An ester is where we have this carbonyl, but then we have another oxygen and another part of a chain. So that is called an ester. Methyl acetate is a simple example of a simple ester. And an amide group here is where that carbon is attached to a nitrogen. A lot of times we will see this in, well, a simple example is acetamide, but this is what are formed when peptides are made. So in proteins, this amide functional group is generated. So I'd like you to take a second here to determine which of these following compounds contains a carbonyl group. And you will probably want to draw these out and to make sure all of the hydrogens are there and all of the everything that it would make sense. So pause, take a few seconds to figure out which of these contains a carbonyl group. So let's take a look at each of these individually. So if we look at A, I'm going to look at what happens here. So if we have a carbon, 3 hydrogens, that's CH3. Generally, when people draw these out, we'll chunk them into, these are kind of, gives us some structural information, right? The condensed structural formula gives us some of this information. Oxygen in the middle, and then another CH3 group. I'm not going to write that out in full form anymore, though, because we can kind of know that carbon has to have 4 bonds, and that's how it will look. So this doesn't have the C double bonded to oxygen anywhere, right? So this one, no. Let's look at B. CH3 group again. And then we have a carbon. Now there's this oxygen. So if I drew this out and made an oxygen bond and then another carbon bond, we don't have any hydrogens attached here. As you can see, this carbon, there are no hydrogens right here that are in front of the carbon. So that means that we're not going to have enough bonds here if we don't do something different. So let me erase this now. So what I'm going to do here is then we're going to fix this here, and now we have, if I create a carbonyl group here, now this carbon has 1, 2, 3 bonds, and now we're going to attach it to this other CH3 group. And now that all of the bonds, there's this carbon here has 4 bonds. this carbon will have 4 bonds, this carbon has 4 bonds, so we're matching up with how many bonds they like to have. And we've made a carbonyl group. So yes, B is going to be one of them that is going to have a carbonyl group. Let's look at C. CH3, we already kind of know, looking at these groups here, right? Those are just chunks off of it. The hydrogens come off the carbon. We have a CH2, okay, so I'll draw that out. We have 2 carbons here. And if I attach this to the hydroxyl group, then we know we have everything has the complete octet here. This oxygen we always know has those, and we're all good to go. So I don't see a carbonyl group on here, so we're going to cancel that one out. Finally, D, CH3, CH2, and C. Okay, so now what can I do here? A hydrogen and an oxygen. Wait a minute, that doesn't work, right? Obviously, because we don't ever have hydrogen's not going to have 2 bonds. So let's fix that. How can we do that? Well, we can have a carbonyl group and a hydrogen, right? And then that gives us 1, 2, 3, 4 bonds for that carbon. And the hydrogen just has 1 bond, oxygen has 2, so that's going to be happy. Oops, sorry about that. So here's our carbonyl group. So here is our last carbonyl group, and so that one works. So B and D, so the answer is 4 here. So I mentioned before, an aldehyde is at the end of a chain, which means that that's a primary carbon. So it's attached to the primary carbon at the end of a chain, and the difference between that and a ketone is the ketone is going to be attached to in the middle of a chain. So it's going to be a secondary carbon. Obviously not a tertiary carbon, because then that carbon would have too many bonds. So here's another thing to think about. Which of the following compounds is an aldehyde versus a ketone? And so I'll take a second to look at this, and then you should have guessed number 1. Tricky here a little bit because this is a hydrogen, right? But these look all the same. But remember, unless there's a hydrogen drawn there, every corner of a line diagram represents a carbon. So there's actually a carbon here with 3 hydrogens off of it, right? So that's what that means, even though it's not drawn out that way. So each of these 2, 3, and 4 diagrams, there's actually a carbon that looks just like this on the end. So don't get messed up with that. If I draw a hydrogen here, that means that the last carbon on that chain is right here, which makes that an aldehyde. What about ketones? And so I just told you number 1 was an aldehyde. A ketone requires the carbonyl group. We don't have that here. That is an alcohol group that we already talked about, and that is an ester. So we talked about all of these. The only correct one is the second one there. Naming aldehydes. So the simplest aldehydes are known by their common names. For example, formaldehyde, acetaldehyde, benzaldehyde, right? So these are just some examples of those different types of aldehyde compounds. We'll be testing you on being able to name some of these compounds. Again, that last section was just kind of update you and get you kind of up to speed to just remember what you kind of maybe learned last year, last semester. But you should be able to recognize the AL ending of a compound. So if you see that AL ending, right, you should recognize, oh, that's an aldehyde. That's an aldehyde functional group. I know what that looks like, right? Being able to identify that end component, that should be familiar to you. So aldehydes, or formaldehydes, is a common aldehyde, is a colorless gas, and a lot of times it's used to kill viruses, fungi, bacteria. It cross-links with proteins, so it's also useful for fixation of, for example, see this brain here, kind of fixes proteins in place, because it'll take primary amines, primary nitrogens, and it'll make that amide functional group, right? If I have a nitrogen here, it can kind of pop that this region off, and then we'll get that amide functional group. So it's called a crosslinker. So it crosslinks proteins together, and then it makes it difficult for other things to break it down. That's why it kind of stabilizes protein and tissue samples as well. We're looking at ketones. Here's just common acetones, a common ketones. An example is nail polish remover. So again, when these things are out of balance in our metabolism, so when metabolism of fats, when fats break down, we end up making ketone, what are called ketone bodies, and this can cause this kind of acetone-like scent on someone's breath. It's produced by the liver. That condition is called ketosis. It can cause major problems of the kidneys and liver as well. So how do we, again, not concerned that you can name all of these things, but what I do want you to recognize is the functional group and that ONE ending. See that ONE ending, that last name? So if you saw something like this, you should be like, oh, there must be a ketone in that structure. That's kind of what I'm focusing on for this class, as opposed to what we're more focusing on in organic chemistry and maybe advanced organic chemistry. So when you're naming ketones, you generally drop that E and then add the ONE ending and number the chains, always starting closest to that carbonyl bond. Obviously for aldehydes, that's on the end of the chain, so you don't really need to have that number there because it's assumed that it's at the end of the chain. But here with the ketones, you don't necessarily know which side, so you always give the lowest number on closest to the carbonyl group. So some examples, acetone, the IUPAC name would be 2-propanone or 2-butanone, pentanone, 2-pentanone, cyclohexanone, or some proper names for that. All right, so something else for you to do. So if you have your pen and paper out, take a second here to predict from left to right the compounds. Here are butane, propanol, acetone, propanol. Which compound has the highest boiling point? Think about which is the highest, which is the lowest, and why. Why would it matter? What's the difference really, right? Here we have just a chain of hydrocarbons, right? Now here we have acetone and propanol. Here we have the carbonyl groups, and here propanol we have an alcohol. So what do you think is going to have the bigger influence? It's propanol has the highest boiling point, and the reasoning is because we have something that can hydrogen bond, right? We have a hydrogen attached to a more electronegative compound. When we have oxygen and carbon attached, right, regardless of if it's in a chain or at the end of the chain, this hydrogen is not attached to anything that is more electronegative to it. Carbon and hydrogen have relatively similar electronegativities. So there's no hydrogen attached to this oxygen out here, so there's no hydrogen bonding. This can have polar bonds, right? So it can still attach to other things. This is still a polar, partially positive, partially negative. Sorry about that. But there's not a hydrogen bond. And remember, the reason the hydrogen bond is so strong is because this hydrogen has one proton and one electron. And when the electrons are being pulled this way, right, it gives a positive charge. This is essentially ends up being a really bare proton in the back end here, and so that becomes a very strong positive charge. So if we're looking at the properties of these things, aldehydes and ketones cannot hydrogen bond with one another. If they are in pure solutions, they can't hydrogen bond with each other. So that's generally what I'm talking about if I ask you, can these things hydrogen bond? You're like, oh, well, a water molecule can hydrogen bond with it. No, that's not what I'm talking about. When I ask you if something can hydrogen bond, I want to know if that thing has the capacity to hydrogen bond, not that something else could bond to it. I want you to tell me what this molecule can do, not what other molecules can do with it. So because of that, they're have generally lower boiling points because they don't have that very strong intermolecular force. So for example, if we look at butane, propanol, acetone, propanol, they have relatively similar masses, right? But their boiling points vary. If we just have butane, it's about 0 degrees Celsius. Propanol and acetone, then that increases to about 50 degrees Celsius. But then we double that even when we get to propanol with that hydroxyl functional group. So here, take a second to then, which of the following compounds do you think are now soluble in water? So take a second to think about that in some of my statements I just made. And the answer is all. The reasoning is, right, we were talking about, well, let's go back to this slide. These cannot hydrogen bond with other things. But water, because we have this partial positive, partial negative, there's still polarity here, and that polarity allows water to interact with this. As long as they don't get too big, as long as these chains don't get too out of hand, right, then water can kind of surround this and solubilize it. Once these chains get too big, then that becomes more difficult. But in the case of these smaller substances, they're all able to hydrogen bond because these oxygens are involved, and then we're able to interact with water. So simple, small aldehydes and ketones are water soluble. We'll talk about some of these aldehydes and ketones in our bodies that are water soluble. It also helps sometimes when they have hydroxide functional groups attached to them as well. So simple ketones generally less toxic than simple aldehydes. That end group allows the aldehydes on the end group allow more things to attach to it and bind to it. It's easier access for that. So they're generally more reactive. Like I was mentioning with those aldehydes, they can interact with primary nitrogens, primary amines, and create those amide functional groups. Many aldehydes and ketones also have very distinctive odors. So a lot of fragrances and flavoring compounds will have aldehydes and ketones, and those are things that can interact with your nose, and the receptors in your nose actually give the different compounds and foods we eat those different fragrances and flavors. So as I mentioned, aldehydes are more reactive. Aldehyde oxidation, there's a hydrogen bonded to the carbonyl group, so it can actually be oxidized as well. So in addition to that nitrogen reaction I was mentioning, oxidation, we can change an aldehyde to a carboxylic acid by replacing that hydrogen with hydroxide. Now ketones obviously can't be oxidized any further because they're in the middle of the chain. That carbon has as many oxygen bonds as it's going to get, and so there are generally no reactions with ketones and oxidizing agents. We can also do the opposite. So the opposite of oxidation is reduction. So those carbonyl bonds get reduced. If I have an aldehyde with a reducing agent, so the opposite of oxidizing agent, right, I can actually change that carbonyl group into an alcohol. So it's a simple way that we can actually make primary alcohols by actually taking aldehydes and reducing them into alcohols. Ketones can also be made into secondary alcohols by reducing them with a reducing agent as well. Here's the result of these two different reactions. I want you to predict what is going to happen. So take a second to read the options, pause, and resume when you think you've found your answer. All right, so if we're going to reduce this, remember which way we're going. We're actually going to turn this into a alcohol. right? Because we're reducing the number of carbon oxygen. So this is going to be a primary alcohol because it's on the end. It's on the primary carbon or primary carbon. Now, if we oxidize this, we can oxidize this because this is an aldehyde, and then we would add an OH group here. That would make it a carboxylic acid. So the answer to this one is number 1 here. Primary alcohol, B is going to be a carboxylic acid. Now let's look at this other reaction. Here we're looking at a ketone and with a reducing agent and an oxidizing agent. Pause, see if you've got this right. Okay, so if you've unpaused this now, here we're going to look at what can happen. We're going to reduce this. We're going to reduce carbon to oxygen bonds. Carbon to oxygen here is going to be then an OH group, right? So we can add secondary, it'll be a secondary alcohol because it's on a secondary carbon. So we're not doing number 1 anymore. That's a primary alcohol. It's going to be secondary alcohol, so it's got to be 2 or 4. Oxidizing reagent, we have to increase the number of carbon-oxygen bonds. Carbon has 4 bonds already. There's not a hydrogen we can get rid of. We can't pop off a carbon, so there's going to be no reaction here. So the secondary alcohol for A and no reaction for B. Here's another really actually important chemical reaction that happens in biochemistry quite a bit, actually. And the reason for this is that we have different types of sugar compounds that can be aldehydes or ketones. And then we have a lot of times those sugar compounds also have many alcohol or hydroxyl functional groups hanging off the side. So what can happen is we can actually have this, what's called a hemiacetal or acetyl functional groups form. So a hemiacetal is in both a hydroxyl group and an OR group is bonded to the same carbon. So we have this carbon, O, and then R group, and then carbon OH group. So you'll notice that functional group, basically what's happening, this partially positive, partially negative region is going to interact with this partially negative, partially positive region. This oxygen is going to be very attracted to that carbon because it's positive charge. And that's why what you're seeing here is this blue group here, this blue group here. This is going to kind of float off, and the electrons from this double bond are actually going to be attracted to that positive charge. So that's why we get this hydrogen is going to allow that oxygen to form, this carbonyl oxygen to form an alcohol, and this oxygen is going to bind underneath to this carbon to actually form that hemiacetal then. And this hydrogen just flips back down to the bottom. So you can see here kind of the simple way, and actually this is maybe a little more easily drawn out for you, is where we kind of have this kind of bent at a 90-degree angle, so you can kind of see what's actually happening a little better. This oxygen partially negative charge is going to interact with the partial positive. These electrons are going to flip up and attach to that hydrogen, and this bond is essentially going to break between the hydrogen and the oxygen, so that the oxygen will still maintain its 2 electrons. So normally, right, we have those lone pairs of electrons, and this bond will essentially, right, oops, sorry, should have another set. These electrons right here are going to be interacting with that carbon. These electrons are going to come down onto the oxygen and be the new lone pair over here. And these electrons are going to flow over here and bind to the hydrogen. Generally, hemiacetals will revert back quickly to the aldehyde or the ketone that they came from. At equilibrium, normally with small hemiacetals, when they're present in a solution, then they'll revert back to ethanol and acetaldehyde, for example. One of the exceptions occurs in biochemistry a lot when it's actually part of the same compound. This is an example of glucose. And as I was mentioning, that's why this is an important biochemical reaction, because we have this, what is it called? An aldehyde, right? It's on the end of this chain. This is the glucose molecule. And you can see there's a lot of hydroxide groups on almost every single carbon on here, right? Every single carbon has a hydroxide on it. This chain actually is formed, right? A lot of times, why do we see it in the long form and the short and the circular form? Well, it's a hemiacetal form when this carbon right here allows this hydroxide functional group to bond to that carbon. So now we have that OR group here attached and an OH group, so we have a hemiacetal group here. So this was the original carbon now attached. So that's why we draw glucose sometimes as a cyclical structure, and sometimes we can draw it out as a long chain depending on what we're trying to show. But then this is actually pretty stable because it's actually a 6-membered ring. We know about the stability of those rings, and it's on the same molecule. So back here, right, if I have an ethyl molecule attach and then detach, well, this can just float away and get out of the way. But here it's kind of stuck there, right? And it's a good stable structure as well. So we can further react that hemiacetal to form an acetyl group with an acid catalyst. So this is just the initial hemiacetal formation that we just had gone over previously. And then if we have another group, another alcohol here with a hemiacetal and an acid catalyst, we can actually basically replace, right? This is a substitution reaction. We're substituting this R2 group with the hydrogen group. So then we're actually forming water, and we've substituted that R group over here with that oxygen on that oxygen. So I want you to figure out based on this ball and stick diagram, which compound below is an acetyl, the structure on the left or the structure on the right. Yeah, so looking at these, there can be kind of difficult to kind of think about what these are, but remember there's a color-coded way of doing this. These black balls are carbon. These are hydrogen compounds. So you have a carbon-carbon, and red is oxygen. So this we have that OR group, the O and the R group here, and then we have another carbon and an OR group. So this is the acetyl over here for sure. So there's one on the left. Let's look at this here. And if we look at this functional group, that's an alcohol. So here is the OR group and an alcohol. So this is a hemiacetal. So on the left we have an acetyl. On the right we have a hemiacetal. So really the only one that is an acetyl structure is on the left. What functional groups are present in alpha-D galactose, shown below? We look at these, we should see that there is an alcohol, 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 and an O. The OH, the carbon, is attached to an OR group and an alcohol, so it's a hemiacetal. So it's a hemiacetal. So the answer there is the alcohol and hemiacetal, number 4.